Okay, good day everyone. So today I'm going to do something slightly different than my standard fare on this channel. I won't be doing a demo of yet another tracking algorithm, nor would I be doing a simulation of an interception algorithm for drones. Let me show you what I actually, let me save that. Let me show you, let's do that. Okay, this is what I'm trying to do. Let's transfer that to the bigger screen. Let's see. Okay, that works good. So a little bit of context. What I'm trying to do here is I'm going to reverse engineer. Maybe I'll say quote unquote reverse engineer here. So reverse engineer what the system does. So what you're seeing on the screen is the display of an part of an air defense system. And so I'm trying to reverse engineer this to figure out what it can do, its key features, observable characteristics, and maybe its limitations and constraints using this video. So again, this is reverse engineering would be a stretch here, because reverse engineering implies that I am trying to make something similar or a copy of the system, just using something like this video. Normally reverse engineering is you have the actual source code and then you work off that we're not doing that here. That's an order of magnitude harder. This is going to be simple, and again, of course, very limited because I only have a 30-second video to make judgments and observations. So that's so yeah, yet another context. So this video is something I picked up from the internet maybe 2-3 weeks ago, and if you've been following some of the defense or military YouTube channels, you might have seen this. This is an Iranian air defense system, or portion of it, and it's tracking a drone, as you can see there. That's near the center with the orange box, and then you have this rain of boxes. Those are actually tracer bullets from an air defense anti-aircraft fire, and clearly they missed, and then followed by this little dot, and that's a surface-to-air missile, and then those are the debris scattering around. So that surface-to-air missile is, at least from what I gathered from this video and other sources, is what's known as the missile 358 or maybe 359, I'm not sure. And so that missile is the Iranian military's reliable or kind of successful surface-to-air missile, and it's been tested against multiple interception against unmanned drones, and so presumably again this is a drone that's being intercepted here, and you can assume that this is a low-flying one because of the anti-aircraft fire. Otherwise they wouldn't have seen them here, and so yeah, it's again a successful strike, taking down an unmanned drone there, which are typically slow-moving, and which is what this missile is for. So let's try to reverse engineer that, and again, as I said before, maybe quote unquote on reverse engineering, given the limited information that we have. And I'm not going to analyze this from a defense or military technology point of view. I'm purely going to take a look at this from a purely computer vision angle, just comparing these against computer vision techniques that I'm aware of, that I know, within the capability, of course, of the things that I know. And again, here I'll also say that I'm not necessarily an expert on computer vision. I do know quite a bit because I have been studying this topic for some time, but again, limited expertise. So given those disclaimer, let's start. So here, what you can see on your screen is that drone being marked by an orange box, and it actually tracks it very well. But this is not hard. If this is your video feed, this is super simple. Any beginner, even beginner computer vision enthusiast or computer science student studying computer vision would be able to figure this out very easily. And it's simple because the background is fairly consistent and flat. You have a little bit of a color shade gradient from maybe the top left to the bottom right. So you can see the top is brighter than the bottom, and a little bit left is brighter than the right side. The gradient might be something different each time, but in this case that's what we have. But it's no big deal because the target is very much different from the background. And here I imagine this is an infrared image, and the target is painted as warm or hot. And so again, it makes it very clear, and maybe the background is cleaner because of the infrared input instead of optical input. So there's then that green box that kind of follows it around, which is a little bit of lag. I'm not sure what it does, but it's there, and then it kind of overlays. Actually, as you can see, it overrides the, if I rewind it slightly, it overrides the horizontal crosshair portion of it, and that's that. I paused it because I wanted to actually start from when it first. Okay, let's start here. So let me mark. So we have no problem in tracking that, and it's easy. But now let's start tracking the tracer bullets here. So let me mark one. So if you can see that there's a little bit of a speck of dust, a white clump of pixels that's a little bit different from the background. So we know it's something, it's the object. And so the algorithm is really just following that around. And if I do that, it's now here, and then we lost it, and then it's recovered here. So that's the path of the target. So let me rewind it back. So I can imagine that the system is actually quite sensitive, because when you're trying to detect a particle or speck of dust, let's say particle in this case, against some background, you want a little bit of contrast from the target from the foreground to background, just so you can say that, oh yeah, that's an edge maybe, and that's potentially an object. There may be other methods that you can do, but let's assume that this is just pure visual, and I see this contrast between the background and foreground. So that's actually super very similar to the background. So if we say let's say if we say the gray is on a scale of 0 to 255, and I'm going to just use this number just for explanation. So let's say the background is at the 100 value level, and this one, because it's super white, it's maximum at 255, but this dot here might just be 105 or 110. So there's a very small gradient at which you can declare the difference between the background and foreground. But visually here we can see it, right? It's no big deal either. There's still a visible gap, and if you convert that to pixel values, it's going to be the same. We'll be able to make the judgment. The problem here is if there's a lot of noise in your input feed, and so maybe it's part of the system or the hardware, or maybe just the background being messy, you might get, and a good example maybe is, let's say, salt and pepper noise. Computer vision people would know what that means, for those that are not familiar. So imagine if you watch old movies, where black and white movies, and then you have these specks of kind of dirt or particles or dust that's floating around, and they would appear for a few frames, disappear, and then there's another one that's appearing somewhere nearby, but they're actually all over the entire frame. That's salt and pepper noise. There are other types of noise, but let's imagine that's that. So if you have that noise in a frame, your tracker would then kind of treat those as also targets. So now you have false negatives. You have false positives. You're saying that there's a target there, there's an object there, but there's actually just part of the noise in the image. And then if you try to clean it up, there are algorithms that help clean it up. But if you do that, you will realize that you will actually see that it will also clean up that actual target. So now you would have false negatives. So what I'm trying to get at here is this balance of figuring out the real object versus noise from your input feed. Maybe it's actually just from your system getting some noise, or it's part of the actual background image. That's the hard part, and that's where you would have false negatives and false positives. And so here maybe it's helped by the cleanness of the input image because it's infrared. But yeah, just one thing to note, this is super sensitive, and it's also able to probably clean the image. So that's actually pretty good in this case. So let's move on, right? But we can also see that sometimes it disappears, just like now. That target completely disappeared, and now it reappeared here. And as you can see, that's an even worse blurred target versus the other ones like this one. And yet it's able to detect that. So that's clearly a good capability. But I'll say that maybe what we're seeing here is actually kind of a, let's say, sanitized, declassified image. Maybe the actual system actually has really clean image with good contrast, and so of course the system will be able to pick it up from there. And maybe this is just a sanitized image, it's blurred, so it makes it look like it's super sensitive, but maybe in reality it's not. But just judging, again, we're limiting our judgment just on this video. It looks like it can pick up blurry images here, here, and here. So that's pretty good. Now let's move on. Okay, let me maybe move this one frame. So again, easy to track, easy to identify, there. That one is fuzzy. I also noticed that there are different sizes. Normally if you do object tracking or study object tracking or see some code, normally they would put a bounding box here. So a bigger rectangle here, and then maybe this is just a square, and then this is a much more square. I don't see that here. I'm not going to assume that they don't do that. Maybe they do, and actually I think they do later. But one way to improve your efficiency is to actually not calculate the bounding box. So here is just putting in same size target marker or object marker, just to make the calculation faster and simpler. Because if you try to estimate the size of the target of the object, that just imposes an additional calculation computing burden to your code. It's not a big deal if, let's say, you have 10 targets. You can very quickly, if you're using OpenCV Python, there's you look through the contours that you pull out, and then you do a bounding rectangle calculation around it. And again, these are just pre-made function calls in the library, and based on the returned coordinates on the box, you can then draw little marker around it, and it works. It's actually not bad. It's fast. Can handle maybe, I don't know, I'm making this up, maybe 30 without affecting frame rate. But let's say that you are actually dealing with much more noisy input. So now you have 300 objects that you're trying to estimate the size of. So now your processing time increased tenfold, and so maybe earlier with 30 objects you're able to keep up with the input of your camera, but at 300, 10 times slow down, maybe you'll get delayed. And so yeah, sometimes you would have to make a call even if it looks good, and maybe it's part of your algorithm to estimate the size. Maybe at some point you would have to make certain thresholding limits where you don't want that part of the logic to kick in, especially for real-time systems. For offline processing, let's say if you tell me that I have 2 hours to process this 30-second video, yeah, sure, I can do all sorts of algorithms to do the proper tracking. But if it's real time, yeah, you'd have to make certain compromises, and that's the beauty and the difficulty of real-time computer vision. You know, you can do it in a given time, but you would have to be very sophisticated with making the right choices and compromises to get things right. So moving on. So let's backtrack. So number one, there's some level of sensitivity on this system, which is pretty good, and it's able to probably separate this from noise without sacrificing a lot of false negatives. And then it's also potentially avoiding size calculations. And then finally, I think the next one is, well, I call this an object tracking system, or let's say, target tracking system. I suspect that this actually is not a tracking algorithm. I am somewhat more convinced that this is just an object detection algorithm. Again, that's the distinction between tracking and detection is known by those in computer vision. But for those who don't know, so the difference really is, detection is where you're given a single frame and you try to figure out where the objects are. Here, finding out the dots. Tracking would involve matching which dot from the previous frame belongs to the current dots in the current frame, and you do that for over time. And of course, it's going to be a little bit more harder that way, because you need to track the location of that. You have to maintain an inventory of the particles, so you would have particle IDs. It helps you a little bit, because if you track the motion of the particle over several frames, you can kind of guess where they would appear next, so you kind of localize your scan there. But normally in computer vision, you would label them here, right? You would put an ID for that particle, so maybe the primary target is particle 1, and then this would be 2, 3, 4, and so on. And then you use that, and then based on the different frames, you then resolve which is which. And that's also a fun part, because you might have objects disappearing, so then you now have to resolve. Let's say you have initially 10 targets, and then 2 of them disappeared because they became hazy on the image, so now you have 8. So now you have to resolve the 10 targets that you have to the 8 remaining. And so your algorithm would have to make choices, maybe based on the closest distance of propagation, and make elimination from there. That's not a hard problem, because there are known algorithms again for that with different uses. But here I'm thinking that doesn't apply, because primarily number one, I think, is just detection. They're not using this for tracking. You would have a different one if you have a sensor that's part of the seeker of the missile. That one most likely would have a tracker to help it figure out things. But here it's just detection of threats, so there's no need for tracking. So I'll stop there on that part. Again, I cannot say it conclusively, because maybe if it's not showing a label here, it's actually just tracking the label without showing the display. That's also possible, but here I'm just making that rough claim. So let's move on to another observation. I'll point this one here. That's two objects with two boxes, and let me move forward. Okay, so here that's still two objects, and we know that because the thickness of this box is too wide versus, for example, this one. So we know that as two boxes overlaid next to each other. But notice that when I then kind of move forward, I don't know if they're on top of each other, but I think it's overlaid, because they cannot be on top of each other because these two circles are separated. So you should have seen a thicker border. So one of them is lost. And it's still one box. And now this one is probably two boxes. And then if I continue, that's again one box, two boxes. So here, what might be happening is it detected that circle, and then it might also have detected this circle, but maybe the algorithm says, okay, they are next to each other, so maybe they are one object. So there's going to be a threshold in terms of distance, that if two separate objects are near each other within a threshold, that they should be treated as one object. And you can kind of tell that this box here, the center is kind of the midway between the two, and I think that's what it's doing. So it's kind of saying, okay, it's one object. However, if you look at this one here, that's also two dots that are near each other, and notice that this second dot here didn't get a box. So these two are being treated as one object. And you can say, well, maybe it's dim, the second one at the bottom, and this one, that's why it couldn't be found. But actually, if you look at this guy here, it's actually dimmer, yet it has a box. So there's again another part of the algorithm that says, and notice also that this is really separated versus this one. So you couldn't say that, yeah, it's using the same logic to declare one object, because this is too far, and yet this is being treated as maybe part of that. So if I move forward, so now at some point it said, yeah, that's a separate one. So maybe earlier that detection, this guy wasn't detected for one reason or another, even if it's brighter than that. And then at some point it says, oh yeah, actually this separate object. So then, and now it says, oh yeah, it's again another object. Maybe my guess here is, if it gets too near, it has a different threshold of what it declares as another object. That's why it's missed again. So that's just another complication in terms of detecting particles, because at some point you have to make a choice. And here, if it's nearby, this is actually kind of a good example also on backtrack. Here, they are treated as one, but the box here is actually just centered on that upper dot, whereas this one here, they are centered, I think, somewhere in the middle. So there's doing it, the algorithm is probably doing some weighting. So it weighs the intensity probably of the light and says that's the center of the object. That's my guess here. I guess again, I haven't seen enough, but that's a fair possibility. So let's move on. So let's backtrack. So we have the sensitivity in terms of contrast. We have a guess that maybe this is not a tracker but a detector, and then we're also saying maybe it's skipping calculation of the object size at some point. And then now we have this algorithm or threshold choices in when two dots are near each other, and then the algorithm decides whether they're two separate objects or not, maybe based on illumination and a combination of illumination and maybe the distance between them. So that's just observing from what's happening on screen. And so that's similar to what we had earlier, where, let me rewind it just so we can see its evolution. So I think it starts from here. So here, two objects, I can see the boxes, and then when I move it, one is lost. So that's kind of weird that it's lost. and then they're just merged into one box, and then now it's completely, the other guy is completely captured into that same box because it's getting closer. So this one, at this point, it kind of say, okay, that's close enough, so maybe it's one object. It's okay, I don't have a problem with that. But earlier they were much more separated up there. So with that, let me play some more. Yeah, again, nothing different from what we've already covered. And let's now check out this guy here with the missile. So detecting this and this, no problem, even if there's this gradient change from here to here, because this clearly is much warmer in the background. So I'm not going to, any programmer in computer vision would have no problem with that. So let's get closer to the target. And so you have two boxes there, and still two, and then now we have one. So as I said earlier, there's potentially some algorithm there that says these two are part of the same object, and maybe it's bounding box, I'm not sure. And again, bounding box is, as I said earlier, calculation. Bounding box could be just contours and outlines, and then drawing a bounding rectangle, or you could have a more complicated one, which is a little bit slower, called connected components. So it basically traces. Anyway, it's not particularly useful in this case because I suspect that it's not needed as much. So let's move on. There you go. So backtrack. There we are. Explosion, and then the tracking box shifted to highlight that guy, but it actually didn't highlight this other clump of light, nor that. So it just targeted that, and that's fine. What's interesting to me is it completely did not track that. So it's possible that there's an illumination threshold, that if it's something much brighter than that, or some other number, if it becomes too bright, that it's considered not an object of interest, and so therefore the marker goes away. And because sometimes maybe you're facing the sun, therefore you don't necessarily want to track that because it would overwhelm, appears too hot. But if we then continue, it's hot, small, again not marked, but and then you would have the debris floating around being tracked, and it just starts appearing everywhere. But notice this guy here. Keep on watching this cloud, the explosion cloud there, and that's still super hot gases. At some point it will kind of separate there. You see this separation here forming two clouds. So that's then it's important to note that, because so there's still the separation, and then at one point you have a separation here too. So now it's going to almost three independent clouds, and all of a sudden you will see here, now that's tracked. That guy is now detected. And I am not sure what's the algorithm doing here, because earlier that's also separated there, and all of a sudden it's almost the same, and it detected that. So maybe there's an algorithm that tracks consistency of the same thing over frames, and then if it's still the same thing and it thinks it's an object, it's a separate object, then it just marks it up after some time. And maybe the other solution, my other guess, is the size of the target. So if I rewind this to that explosion, right? So here on the explosion, it's the gas cloud is very big, so the object would be wide, and so maybe there's a cutoff that says anything bigger than this do not track, which goes back to, that's why I said earlier, I'm actually not sure whether this accounts for sizes as well, because maybe here both illumination and or the size are used to eliminate false positives. But notice that that's kind of not very big, right? Well, it's a circle, a big one. But if I do this, that is arguably much more surface space, surface area than that. Yet this is not marked, but this is. So I don't know if this is being eliminated because of the illumination, but I think the size is also used to eliminate some targets. And here we see that there's actually two clumps, but it's not able to resolve this gap here in the middle. So it treats this two as one object, but even if it's treating these two as one object, it actually doesn't go to the centroid because normally the center would be around here, and so your bounding box would be around that, enclosing that circle. The bounding box is actually centered around here on this gas cloud, without accounting for this guy here. And so there's some specific algorithm here again. And I'm not saying this is the right behavior. Maybe the right behavior would actually be to form two boxes, one for this and one for this, or the other behavior might also be a box that's here. I'm just saying that this is how the algorithm is behaving, and this is very often what happens in computer CV algorithms. You write code that works in one video, and then you're fine with it, and then you run it in another video, it doesn't really work. But here, you just have to, in a way, accept the limitation of your system. That if you're using this to track a target, you'll get this guy, but this guy escapes. Or if you have a weighted centroid, you might be targeting this one, and then basically both this one and this target is missed because you're going through the middle, which is kind of a gap. So that's where the judgment of writing many different conditions take the most work. And that's where it's a little bit challenging, exciting, but also frustrating because you didn't keep under engineering your work. It's completely different for those who are familiar with machine learning, of course, deep learning vision models. This one, you can probably train a little bit, but because they are just basically point dot pixel size tracking, it gets a little bit different, and you might have to do some other retraining to get it to work. So if you're doing it the old-fashioned computer vision way, you would have to make these compromises, and so you're basically trading a lot of the quality work and precision for speed. And of course, you have to remember this thing is running at, let's say, 30 frames per second, for example. I think this is running at 10 frames per second at least here, but 30 frames per second, you need to process a frame at, what would it be, 0.033, somewhere there, of a second to cycle through all your algorithms. And so the more targets you track, the harder it will be. So you have to really clean up the image and make certain compromises and accept the quality of the work after. So that's, I think that's the last of what I have to say. So just closing down. So we started with the sensitivity in terms of detection. Like this guy here can detect that, but there's nothing there, but yet still it targeted that. So now I do not know whether this is actually a false negative or false positive. So that's that one here. And then we also said that this is likely not tracking, more leaning on detection. Also consistent with the purpose of this system, which is just to detect incoming threats, not to follow incoming threats for destruction. And then I was also guessing about the absence of size estimates of targets, because that definitely takes a lot of compute cycles. But also I said maybe at some point it actually uses the size, at least on the bigger ones, to eliminate big targets. I don't think it uses it for smaller targets, but well, therein lies the difficulty, because how do you know that the target is small if you are not doing size comparison, size check to begin with? So maybe there's a faster algorithm that says, okay, this is a dot, and then once you encounter something that's a bigger clump, you then apply a much harder algorithm to establish whether that's one target, bigger target that has to be excluded, or something that's useful to track. Because, for example, here you probably have a certain size of drone based on distance, and so you can make adjustments based on that. And I think, what else did I say? And then you have the algorithm to decide whether two separate dust particles compose one object, or whether there are two separate objects to track. So again, those are additional things that your algorithm would have to work out for. So given that, yeah, I think at least for its actual purpose of tracking the drone, which is reasonably sized target, it works. I was actually just surprised that it could track the tracer bullets, but then I realized that actually, yeah, it doesn't need to have a lot of precision on the small ones. So it's just detecting anything that goes into a certain level of a certain window of threshold and parameters, and then put a box around it. But that's not the critical part. The critical part is to identify the most likely targets in the middle, the approximately medium-sized drone, and that's that. It took longer than I would have expected, but probably I did quite a few diversion side explanation. But yeah, this one really, when I saw it, I thought, oh, this is pretty cool. This is not hard to make. But then when I looked at it, I know that, you know, if you make this, you would have to make certain compromises. And so if I make something similar, it wouldn't function exactly the same as this one. It might have worse performance in terms of detection, but it would probably make less mistakes in terms of false positives. So you'd have to just do certain adjustments. And also, without seeing the actual input from the system, I wouldn't know where to put the sensitivity threshold. But yeah, maybe in the future I'll make up some test video, and the test video should not be too difficult to make. You basically just make moving salt and pepper noise, not purely salt and pepper, but you would have salt and pepper looking moving particles, and then you're supposed to track them. So that's not too hard to self-generate and then test some algorithms around it. And yeah, it should be fun. But I'll stop here. I think it's good enough. You've seen this run through, and if you're a CV person, you definitely notice the techniques just by looking at this video. What surprises me is actually, this is of course military technology. I suspect it's much more complicated and sophisticated than that. But as a CV enthusiast, you can certainly detect the techniques used here, or at least guess the techniques that the developers used here, and in a way, one could make a similar system of more limitations perhaps. But yeah, if you just want to make something, you can definitely do this single-handedly without a lot of need for heavy duty hardware. So with that, I will end here, and that's it. I'll see you on the next one, and good day once again.